Now, if you remember, there were three cases: the case of real distinct roots, the case of real repeated roots, which we've done both of those, and the third case is the case of complex roots. So we'll do an example of that as well. That occurs when this number b squared minus 4ac is negative. And as an example, we'll take y double prime plus 4y prime plus 13y equals 0. These numbers that I've been putting in here have been chosen just to make everything work out in integers. So there's no real reason for choosing them other than the answers that they give are a bit nice, not too bad to write down. All right. So let's proceed as we've done before. We'll try y is e to the lambda x, and we get our, we substitute in our y prime gives us a lambda e to the lambda x, our y double prime gives us lambda squared e to the lambda x, and so we get lambda squared plus 4 lambda plus 13 is equal to 0. That's our auxiliary equation or characteristic equation. Right, the roots of that, well, we can try and factor it. So in this case, you can't factor that equation, but we can use the quadratic formula. So lambda is minus 4 plus or minus the square root of, well, b squared is 16 minus 4 times 1 times 13. 4 times 13 is 52, all divided by 2. So 16 minus 52 in my books is 36, minus 36. So it's minus 4 plus or minus square root of minus 36 divided by 2. So here is where our complex numbers are coming in. Square root of minus 36 is 6i. So it's minus 4 plus or minus 6i divided by 2. Remember, I is the square root of minus 1. And we can divide that by 2, and we get lambda is minus 2 plus or minus 3i. And that's the reason for choosing 13 in this last position, is it's given us integers for these solutions. So I'm going to need a bit more space. What I'll do is I'll just erase this and write it. Up here we've got the roots are that lambda is minus 2 plus or minus 3i. Now, at this point, there's no reason that we can't write down the solution that we had before from the real case. Remember, we had two roots, lambda 1 and lambda 2. We had a general solution. Y is c1 e to the lambda 1x plus c2 e to the lambda 2x. Well, we can write that solution down as well. Y is c1 e to the lambda 1x. So let's say that's minus 2 plus 3i times x, plus c2 e to the lambda 2x, so it's minus 2 minus 3i times x. And there's nothing wrong with that as a solution of our equation, except for the fact that it's a real differential equation, and we probably have real initial conditions, and so we would like to have a real solution. Now, this thing may well have a real solution. It depends on your choice of these arbitrary constants c1 and c2, and if you're careful about them, you can indeed make this solution be purely real. But it would be nice if it was a bit more explicit. So what we'll do to make that explicit is to transform this exponential here. It's an exponential of a complex number. We'll transform that using Euler's formula. So let's see how that works. Let's just take, for example, that first one, e to the minus 2 plus 3i all times x. Well, okay, I can write that as e to the minus 2x plus 3ix, just multiplying the x into the brackets. It's the exponential of a sum of two quantities, which is equal to the product of the exponentials of those two quantities. So it's e to the minus 2x times e to the 3ix. And now this is where we use Euler's formula. E to the minus 2x is perfectly sensible as a real function. E to the 3ix, what we'll do is we'll write that as a cosine of 3x plus I times the sine of 3x. Okay, so this function here then is equal to e to the minus 2x times cosine 3x plus I times sine of 3x. All right, so what this is saying, now if we do the same thing for this one, we'll get the similar equation. So everything works the same except it's minus 3i, here it's minus 3ix. So this is cosine of minus 3x plus I sine of minus 3x. Cosine of minus 3x is the same as cosine 3x because cosine is an even function of x. Sine of minus 3x is minus sine of 3x because sine is an odd function of x. And so we get the same expression, but with that plus changed to a minus. Now, if you're careful about your choice of constants, what you can do is arrange for these i's all to cancel out. And the details of exactly how that works are a little bit long to write out. They're not terribly difficult, but a little bit long to write out. And the end result is that your general solution is going to be y is e to the minus 2x. And we've got these cosines and sines. We've got arbitrary, c1 times this with a plus and a c2 times this but with a minus there, which means that we've got a c1 and a c1 in here with a plus, and we've got a c2 and a c2 in there with the minus. We bring all these things together, and we're going to give new names to our arbitrary constants. So let's call it, say, a1 cosine 3x plus a2 sine 3x. Okay? And there it becomes a little bit clearer that this is going to be a real function of x. As long as we choose a1 and a2 to be real, and no reason why we shouldn't, this y of x will be a real solution of this differential equation. So in general, if you've got a characteristic equation that's giving you complex roots, if we call this, say, p plus or minus iq, then you can go through all this argument, but if we cut straight to the end, the general solution will be e to the px times, say, a1 cosine qx plus a2 sine qx, where p and q are the real part and the imaginary part of this complex root. And that's the general solution of this second-order differential equation with complex roots. I'd like to finish this section with a very brief discussion of what these functions look like as a function of x. In the case, because they have names that are related to a particular mechanical system where these kinds of equations come up. If you've got a spring and some kind of friction device, and possibly a device that's known as a dashpot, so basically the shock absorber of a car is an example system that is governed by a differential equation like this. It comes, its behavior will be different depending on whether the roots of its differential equation have real roots, real repeated roots, real or complex roots, the three cases we've talked about. In the case of real repeated roots, you'll get exponential decay. So that is called, gets a name, it's called overdamped. So here, now instead of x, we're thinking of a mechanical system, so the independent variable is time. But if we've got the case where real distinct roots, so that means solutions like e to the lambda 1t and e to the lambda 2t, where for, say, the shock absorber of a car, these lambdas will both be negative, then you'll get solutions that will decay exponentially in time. So that means you give your car a bump, and your car will gradually restore itself to its equilibrium position. And this is called overdamped. And if your car is doing this, it's not tuned properly. this is the case where our b squared minus 4ac is positive. If we've got the case where b squared minus 4ac is equal to 0, then the graph of the solution of our equation as a function of time is turns out that it's still exponential decay, but it gets there more quickly than the overdamped case. So this is called critically damped. And here we'd have roots which are just lambda. So our solution is e to the lambda t and t e to the lambda t. And the third case is where we have complex roots. And in that case, what happens is your car, instead of, you give it a bit of a bump and its shock absorber, instead of smoothly taking you back to an equilibrium, it bounces you up and down, perhaps with a decaying oscillation. So solutions of that look like this. And that has an envelope of an exponential decay with an oscillatory behavior in the middle. And this is called underdamped. And if your concern is to design a shock absorber, then chances are you want to aim for something like this. And this is the case where b squared minus 4ac is negative. So we have complex roots, which would look like e to the pt with cosine qt sine qt, where remember that because we're thinking of this as a mechanical system, instead of dy by dx, we're thinking of dy by dt. So that concludes this section, this podcast on homogeneous second-order linear equations. And there's another podcast on inhomogeneous second-order linear equations. Thank you.